about related rates. Want to know how related rates affects you? Don't let water down coffee. Drink up. The rate of ice of coffee will water down your coffee before you know it. Also, the rate of absorption of the caffeine in your blood will help you stay up all night.
We have learned that calculus is a study of change. More specifically, it asks the question, what is the instantaneous rate of change of something? Moreover, one of the broad topics of calculus that we have learned so far is differential calculus and how concepts such as functions, limits, continuity, and discontinuity apply and connect to one another generally. Throughout our journey with derivatives, we explored problems in which functions were exclusively given in the form y equals fx. Then we encountered situations where it was difficult or impossible to express y explicitly in terms of x. Such functions are called implicit functions. Related rates involve situations where two or more variables change simultaneously, possibly at different rates. If we know how the variables are related and how fast one of them is changing, then we can figure out how fast the other one is also changing. This usually involves writing an equation relating to the two variables and taking the derivative of the equation with respect to time. Implicit differentiation is often used, then followed by derivative rules as they apply. We have seen that for quantities that are changing over time, the rates at which these quantities change are given by derivatives. If two related quantities are changing over time, the rates at which the quantities change are related. For example, if a balloon is being filled with air, both the radius of the balloon and the volume of the balloon are increasing. In this section, we consider several problems in which two or more related quantities are changing, and we study how to determine the relationship between the rates of change of these quantities.
Hello kids, today we're going to be doing a video on related. So this question states, a 6-foot tall person walks away from a 10-foot lamppost at a constant rate of 3 feet per second. What is the rate that the tip of the shadow moves away from the pole when the person is 10 feet away from the pole? What is the rate at which the tip of the shadow moves away from the person when the person is 10 feet away? Alrighty, so here, I've already drawn out the triangles because this is what our equation looks like, our problem looks like. So we start off with the lamppost over here. Shining the light down, this is 10 feet tall. Now, between the person and the lamppost, there is 10 feet. Little person, that is 6 feet. Now, we have the relationship in between the man and the lamppost. We have that rate, which is 3 feet per second. That's how fast he's walking away from it. And we are looking for the rate at which the shadow is moving from the person and from the lamppost. So we start off with a proportion because we have two similar triangles. We get 6 over x equals 10 over x plus y. So we start solving for x because we're looking for the derivative of x. So you start arranging things. You get 6x plus 6y equals 10x, 6y equals 4x, and at the end you end up with x equals 3 over 2y. We leave it like this because we can't solve it anymore. And now we are going to implicitly derive to find the rate of the shadow in respect to the man's position. Alrighty, so implicitly deriving, we end up with dx over dt, 3 over 2, there's a constant, and dy over dt. We already have dy over dt as this rate over here. So all we have to do is plug in to get our answer. 3 over 2 times 3. This will be feet over second. I'm not writing it because it's cumbersome. dx over dt will equal 9 over 2, which will lead us to a rate of 4.5 feet per second. And now, to find the rate at which the tip of the shadow moves away from the pole when the person is 10 feet away from the pole, we have to just add the two rates. 4.5 feet per second plus 3 feet per second. So now you just end up with 9.5 feet per second. That is both of our rates, here and here. Easy. Now for example 2. So water is being drained from a container which has the shape of an inverted right circular cone. The container has a radius of 2 inches at the top and a height of 5 inches. At the instant when the water in the container is 2 inches deep, the surface level is falling at a rate of 1.9 inches per second. Find the rate at which the water is being drained from the container. Alright, so instead of starting off with a drawing, we're going to start off by identifying the values that we were given along with the rate that we were given. Okay, so the radius is going to be 2 inches, the radius of the cone, and the height of the cone is 5 inches. The water is at a depth of 2 inches from the top, falling at a rate of 1.9 inches per second. Now we can draw it out. So the height equals 5. The radius equals 2. And the water is 2 inches in depth. Falling at a rate of 1.9 inches per second. Alrighty, so here we also have a proportion of similar triangles, which states the following: x over r equals k over h, which in this instance will be cone height over radius equals y over r. So our cone height is 5, our radius is 2, we have y over r. So now we're solving for r. So we end up with r equals y over 2.5. And now we're going to jump to a different equation. This is going to be the equation of the volume of a cone. This one's important because this is what we're going to derive to get our rate, because we're going to derive volume in respect to time. So we already have r in this equation, so we just substitute it in there, which is y over 2.5 squared y. When you mush this together to simplify it, you end up with pi over 18.75 y third. Now, this is easy to implicitly derive to get the derivative of the volume in respect to the time. So you end up with, taking out the constant, because pi is in there, 3y squared, not equals, dy over dt, equals derivative of volume with respect to time. And we have y squared and we have the dy over dt. So we just have to plug in the values that we already have from the beginning to get our rates. 9. Now I've already multiplied this off screen, so we don't have to do it right now with the calculator. So we get 3.88 cubic inches per second. The water is being drained at a rate of 3.88 cubic inches per second.
And now, for another example on related rates, Lorena, struggling college kid, trying to get that assignment due before midnight, and her rate of how fast she can type will determine if she can finish the assignment before midnight.